name is Justas. I'm a final year PhD student, and I'll tell you more about digital twins. Specifically, I focus on buildings, otherwise known as smart buildings in the digital twin context. And we have deployed over 400 sensors in the Williamsgate building across the street. And I'll show you several examples from one of the densest parts of the building, which is the lecture theater. And that particular site has around 40 sensors in it. And these are the findings from my research. So in a way, my PhD really begins over a quarter of a millennia back, when this British philosopher named Jeremy Bentham decides to travel to Krycha, which is a small town in Russia, of all places. And Jeremy Bentham is known for this philosophy that he created, which is called utilitarianism. And it's an ethical theory that says that the best action is the one that maximizes overall happiness or well-being, greatest good for the greatest number of people, sort of thing. And Jeremy Bentham creates this idea for a new sort of prison. It's a prison where a single prison guard can overlook every single prisoner, and without the prisoners knowing that they're being looked at. So basically, it's a sort of optimization on a typical prison. Now, the reason why I'm telling you about this is that if you have a modern smart building like you see here, this is an environmental heat map of temperature in the building. By looking at it, you can sort of find your office and see how warm it is. But the issue arises when we're looking at something like a CO2 heat map. And CO2 tends to spike very rapidly whenever people enter buildings or different rooms. And so what happens is, just by looking at this, you can see when people come into their office, how long they stay in their office. And if you conduct a sort of longitudinal study of that, you would know when everybody is in their office at all times. So you can see how this is starting to resemble the panopticon in a little way. And the issue is that the sort of smart building systems are usually only controlled by facility managers. And one of the questions I try to ask is, how do we actually democratize this data and make it available for everybody? So my general research overview, right? We do a bunch of work on sensor design, on real-time data processing platforms. How do we integrate sensors into this real-time platform? How do we acquire sort of augmented intelligence from all this data by focusing on specific events that happen across the building? We do a lot of work on privacy preservation, obviously, to make sure that the systems we build are actually not privacy leaking at all, and therefore do not violate anyone's privacy. And we do focus a lot of work on end user applications, some of the work that I'll be showing you today. In practice, it has to do a lot about going into one of the lecture theater, for example, deploying a bunch of sensors, going up the ladder, deploying more sensors there, and creating nice, funky real-time data visualizations that depict people and all the data that the sensors gather. So this is an example of a privacy sensing sensor. You can see that these are one of the 3 cameras deployed at the ceiling of the lecture theater. We have 3 cameras pointing towards the crowd. We do face detection, not face recognition, a very important difference. We use a set of neural net-based architectures to detect faces sitting in the lecture theater, and then we localize people in the lecture theater to know where they're sitting based on where their faces are in the photos. The thing about these cameras that make it privacy preserving is that the photos do not leave the devices at all. What we do is we have every single seat allocated a specific string of characters, sort of like you'd find in a cinema. And we basically assign our 0 or 1 values to each of the seats. And then the final output from the cameras is only a string of characters and nothing else. So now we find ourselves in a situation where we have building managers sort of hoarding all that data. And we have really no good way of actually sharing that with everybody else who's in the building and creating all the data for facility managers to look at. And then the way we reverse this process is actually by creating these applications that allow ordinary building occupants and, for example, lecturers, if we're talking about the lecture theater example, to use all that data to get some meaningful information that may benefit their work. And for that, I'll show you 3 examples of that. So first of all, how do we present this information to ordinary building users? So this is an example of a lecture taking place in a lecture theater, sort of a snapshot. This image shows a body heat map radiation heat map of temperature. And what you can see here is that when people are sitting so close together, the air around them tends to heat up quite a bit. So you're actually sitting so close together, you're literally forming these tiny atmospheric bubbles around you. And this was a very important tool to use during COVID, for example, because we wanted to show people that it was actually very dangerous to sit together, not because somebody told them to, but because science says so. And then we can expand on this example by looking at CO2 data. So interestingly, we found that the CO2 distribution in the lecture theater doesn't actually change that much with the number of people. You tend to get two hotspots, one at the bottom and one on top. The bottom one is explained by the lecturer standing there and talking so much, CO2 tends to increase by quite a bit. The top bit tends to increase because CO2, exhaled CO2 specifically, tends to rise, and then it stratifies at the top of the lecture theater. Therefore, some of the worst places you can sit at is the back. And this is a video of CO2 changing during the span of a lecture. So as the lecture begins right now, CO2 tends to rise very rapidly within minutes, and then it tends to plateau, and then it basically stays there until the lecture is ending. So this was one of the communication tools we used during the pandemic to tell people that they should not be sitting close together and that they should not be sitting at the back. Another example is how we actually use the data to empower lectures. So given the placement of the cameras, we collect 1,000 data points a day. Out of those 1,000 data points, basically only need 4. And these are the lecture start and end events. And what we can do at the end of a lecture, we can sort of provide a synopsis, a summary of what's been going on during that lecture to a professor, right, or whoever's teaching. And by using a face up as a proxy for interest, you can actually show people how much attention everyone's been paying during that lecture. So we also find that people sort of paid more attention sitting in the middle, at the back, big surprise, no one's paying any attention. And then at the front, sorry. Now, the final example is sort of data that might be of interest to building managers. So what you can see here, we focus on anomaly detection. This shows a term-long view of the lecture theater being used. You can see an obvious anomaly over here on a Saturday, where too many people showed up in a lecture theater and HVAC was not scheduled to turn on the weekends. This is being shown by an anomaly score, which is a sensor-fused score from environmental and crowd count data. And thus we help find out that HVAC is not functioning very well. But there's another way to look at it, right? If you look at longitudinal data for where the people are sitting in the lecture theater, you see that everyone tends to sit at the back primarily. This is the back entrance. And then there's this tiny weird spot that no one sits, right? And we had no idea what was going on. We went to check it, and we couldn't find anything wrong with that particular seat until one time we went there when it was raining, and water actually dripped on this very seat. So in summary, if you're sitting at the back of a lecture theater, you have nothing to breathe, you're bored, and you probably have water dripping on your head. Right, so given all these examples, right, how do we create a digital twin system that is sort of panopticon-less by design? We first of all have to start with the sensor stack. First, we focus on low-level sensors that use these machine learning systems, and then realize that the impact is actually realized at the very application layer. So the question is, how do you actually create sensors that sort of limit what's actually achievable at the very end? How can we limit this? How can we embrace privacy preservation from the very bottom so that it impacts the high-level applications, right? And this is done by embedding this sort of privacy forward thinking at the very lowest level. And now traveling a quarter millennium in the future again, the question is the questions about the digital twins that we might be building then. And really, we can go from hoarding data and letting someone spy on you, or instead, we could actually focus on democratization of data by creating applications that anyone could use, by creating applications that foster sustainability, that automate these spaces, that maybe turn off the lights when no one is there and save electricity. We can foster autonomy, and most importantly, managing complexity in such future infrastructure projects like space stations. So thank you very much. That's my little presentation, and I hope you enjoyed it.